Before 2017, the standard for processing time series and natural language relied on sequence transduction models, specifically recurrent neural networks, LSTMs, and GRUs. These models generate a hidden state, HT, strictly as a function of the previous hidden state, HT-1. Each step must wait for the output of the step before it. Because of this dependency, computing dependencies sequentially prevents parallelization within training examples. You cannot process the end of a sentence until you have finished the beginning. This linear progression creates an O of n number of sequential operations per layer. Data must pass through every intermediate node to reach the end of the sequence. As sequences get longer, the memory required to maintain these chains limits how much data we can batch together. This O of n architecture creates a hard ceiling for training efficiency and limits our ability to scale models to larger datasets. Researchers from Google Brain and the University of Toronto proposed a solution they called the transformer. It is an architecture that removes recurrent and convolutional layers entirely. To replace them, they use self-attention as the sole mechanism for drawing global dependencies between inputs and outputs. In this new map, the linear path breaks apart. Because all positions in a sequence are processed simultaneously, the number of sequential operations drops from O of n to a constant O of 1. This reduces the maximum path length between signals. In an RNN, signals travel through the entire chain. In a transformer, any two positions connect in a single step, easily learning dependencies between distant words. Removing the sequential requirement enables massive hardware parallelization. Using this architecture, the authors reached a new state-of-the-art in translation quality while using less than 1% of the training cost of previous models. The engine driving this performance is scaled dot product attention. The inputs are queries and keys of dimension dk and values of dimension dv. The model computes a compatibility score by taking the dot product of the query with all the keys. This score determines how much weight is assigned to each value. However, there is a mathematical problem with standard dot product attention. As the dimensionality, dk, gets larger, the dot products grow significantly in magnitude. These large values push the softmax function into flat regions where gradients are extremely small. To fix this, the authors scale the dot products by the square root of dk. This keeps the values in a working range, stabilizing the backpropagation process and allowing the network to learn effectively as the model grows. Instead of one massive attention function, the authors use multi-head attention. The model projects queries, keys, and values into 8 lower dimensional spaces. Attention is performed on each in parallel. The results are then concatenated and projected back. If the model only had one attention head, the process of averaging would prevent it from focusing on different parts of the sentence at once. Multi-head attention allows the model to jointly attend to information from different representation subspaces. It can track syntactic relationships in one head while analyzing semantic meaning in another, without increasing the overall computational cost. Discarding the sequential chain creates a problem. The model now has no inherent way to know the order of the tokens in a sentence. To restore this information, the authors inject positional data directly into the input embeddings. They use sine and cosine functions of different frequencies to create a geometric progression. This generates a unique mathematical fingerprint for every position in the sequence. This trigonometric approach was chosen because it allows the model to learn relative positions. Any fixed offset k can be represented as a linear function of the original position. Positional encoding translates sequential order into high-dimensional coordinates, giving the attention mechanism the context of time without requiring sequential processing. This brings all components into a single encoder-decoder structure. The encoder is a stack of 6 identical layers, each containing multi-head self-attention and a feed-forward network. The decoder is also 6 layers, adding a third sublayer to attend to the encoder's output. In the decoder, the model remains autoregressive, meaning it cannot look at future words to predict the next. To ensure this, the authors use masked multi-head attention. By setting future connections to negative infinity, the softmax function effectively ignores them. This guarantees that predicting a word only depends on the words that came before it. The architecture's effectiveness is visible in the results of the WMT 2014 English to German translation task. This chart compares translation quality against the computational cost of training. Previous models, like GNMT, required massive compute. The base transformer achieved a 27.3 BLEU score, using a fraction of that energy. The big transformer reached 28.4, outperforming all previous ensembles. This was achieved after only 3.5 days of training on 8 P100 GPUs, a significant reduction in hardware time compared to the weeks required by legacy models. The O1 parallelization of the transformer means that extreme performance no longer requires exponential increases in compute time. The technical achievement of the transformer is the reduction of the maximum path length between any two sequence positions to a constant. Attention is no longer an auxiliary tool for recurrent layers. The transformer uses attention as its primary structural component. The authors suggest this architecture can be applied to data beyond text. By using restricted local attention mechanisms to manage the high resolution of images or the duration of audio, the transformer can avoid the memory bottlenecks that affect recurrent systems. Whether the input is a sentence or a grid of pixels, the model treats the sequence as a global set of dependencies. This makes the architecture a general-purpose template for a future of multimodal machine learning.